All right, hello. We are the Swamp Solutions Group for Unit Operations Lab 1, and this is our final poster presentation. To start with our real-world challenge and objectives. So the challenge we're addressing is that in coastal and arid regions, both domestically and abroad, these communities rely on desalination for potable drinking water, but the process is one, very energy intensive, and then two, not sustainable in a lot of cases. And so we want to design a desalination system that is cost effective while addressing what we think are the three key drivers or considerations. The first would be water quality. So we want to make sure that the concentration of salt within that permeate line is drinkable. Two would be energy efficiency. We want to make sure that both during that initial heating and continued pressurization, that the stream must be energy efficient during the process. And the last would be design durability, because we don't want that pressure to cause the membrane performance to drag or degrade over time. And so we have two main objectives. The first would be to design and analyze a desalination system that meets that target permeate flow rate and salinity specification while minimizing energy consumption and costs. And the second would be to evaluate how operating conditions such as pressure, temperature, the pre-treatment concentrations in terms of salt, how those impact performance metrics such as recovery ratio, membrane effectiveness, and the overall cost. And so we looked at three experiments. The first was TFF. This experiment allowed us to optimize the TMP of the system to make sure energy isn't being wasted while running that pump at a greater pressure and to make sure that the membrane isn't being damaged. The second was heat exchangers or HEX. This allowed us to identify the overall heat transfer coefficients for different exchangers and determine which one we think would be best for warming that water in order to lower its viscosity and reduce the pumping pressure or the pumping work required. And the third would be fluid flow or FLU. So the ASME has a 3% non-recoverable pressure drop rule for all relief devices. We have a relief device for the pump and a maintenance valve for the PSV. And so the FLU experiment allows us to identify what valve would work best for the application without breaking that 3% rule.
Now, to go from lab to application, you would first want to use and characterize the memory performance using TFF skills that we learned. And so to do this would include measuring flux at different pressures, as well as running a TMP excursion study and performing pre and post NWP tests. And by doing this, we would be able to see how easily water moves through the membrane, as well as where flux begins to plateau and how fouling changes with performance over time. Step two, you'd want to extract key parameters that we need, and so you'd be able to predict the reverse osmosis or desalination performance that you need to know. So you'll be able to tell how permeable the membrane is, as well as how much resistance builds up and how effectively salt or solutes are rejected. And then step three, you'd want to translate these TFF principles we're using to reverse osmosis conditions. And so this step, you'd be able to really understand what happens in the lab to predicting what would happen in an actual desalination unit. And then step four, you'd want to develop a lab-based testing protocol for desalination. And so this step is where we're asking questions of if this was a desalination membrane, what measurements would matter most, or how we would evaluate performance as well as detect fouling. And then step five would generate water treatment recommendations. And so will be able to estimate how effective the membrane would be at removing contaminants, and just how we track dyes during our TFF experiment.
There were four main assumptions and simplifications that allowed us to move from lab to application. So the first was that the only impurity of focus for now would be the salt concentration. We're not focused on anything biological that could be filtered out later down the line with, for example, boiling the water. We're also assuming that the heating of the salt water is solely to lower its viscosity and to provide an incremental increase in pumping efficiency. The third point was that the overall desalination costs are lower than any transportation costs for clean potable water. This obviously wouldn't make sense if it would be just cheaper to truck in water from a neighboring town or city. And the fourth point would be membrane behavior for that permeate flux as a function of TMP is similar to what we measured in TFF. And so we're essentially assuming that the membranes, in this case for a desalination process, would be similar enough to the membranes used in that experiment in the lab in order to draw comparisons and conclusions.
So looking at translating this to practice is all about looking at our different operating conditions. For temperature of the system, we want to balance both membrane performance and membrane fouling, because at higher temperatures, you're going to get a better performance out of the membrane, but you're also going to increase the membrane fouling, which is increased cost for maintenance. We can control the temperature of the system by controlling the flow rate of heated water into the heat exchanger. The pressure of the system is controlled by the pump, and it's all about basically getting an optimal TMP from the membrane, as we don't want to put wasted energy into the pump and not get any flux out of that, because it's no longer going to be dependent on the TMP. For concentrations, we're going to assume that the water coming in is seawater, which is typically 35 grams per liter. And the desalinated water, we want to be below 60 milligrams per liter because that's safe drinking water levels. And then the equipment we chose for the maintenance valve, we chose a ball valve as it had the lowest non-recoverable pressure drop based on the data we retrieved in the fluid flow experiment. And then for the heat exchanger, we chose a countercurrent shell and tube exchanger because it had the higher overall heat transfer coefficient while also not taking up as much physical space, which we learned in our HEX experiment.
When it came to lifelong learning and professional impact, one of the biggest takeaways we took from Unitops 1 is how many practical skills will carry forward into our engineering careers. Throughout the semester, we had to troubleshoot many unexpected issues, work through uncertainties, and be constantly evaluating whether the models we learned in class were actually applicable for the systems we were working on. These habits were really essential when we applied data from different modules such as TFF and the flu module to our design. Nothing behaved exactly like ideal theory, so learning to validate assumptions and adapt our approach was really important. Working in rotating team roles also reshaped our view of engineering practice. It showed us how much engineering relies on clear communication, planning, and shared responsibility. Every decision we made, whether it was adjusting flow rates, interpreting pressure losses, or redesigning our plan from week 1 to week 2, required coordination and accountability. And this experience closely reflected how engineering teams operate in industry. Overall, this project reinforced that engineering is not really about achieving perfect numbers, but it's more about making practical decisions that, even when the data is imperfect and the equipment has limitations, we can still support. Using real pump curves, pressure drop measurements, and heat transfer behavior to inform our operating conditions made the work feel genuine. And it helped us to appreciate the judgment and safety awareness engineers need, especially when working on something with meaningful real world impacts, such as providing clean water.
These are our references, and thank you for watching our presentation.